Let's have a look at the energy of the charging of a capacitor. This is quite interesting. So we've got our EMF there, we've got our resistor, and we've got a capacitor. Now that's plus, minus, so the capacitor will eventually be plus on this side, minus on this side. Now when the capacitor has eventually charged up, then this voltage will be the same. There'll be no current flow. No current flow, no voltage drop across the resistor. Therefore, the voltage here would be 12 volts. If that's 12 volts, this will be 12 volts. But there's going to be a period in which it gets charged. It starts off, if you've got a open switch and then you close the switch, it starts off with no voltage on it. And so we get these charging curves, which we'll look more at. But for now, we're saying the voltage starts off at 0, and over time slowly increases up to where it gets to the voltage or EMF on the battery. So that's the charging curve for the voltage against time. The current is high at first because at first we've got no opposing voltage from the capacitor. So the current actually starts off high, and it's going to start off at V over R if this is the resistance. So the current tends to do that. Alright, so we will look at those curves in a little bit more detail. This is called the charging curve, and this is called the discharging curve. And this point here, I equals V over R, would be I naught if you like. Now, I wanted to look at the energy of this whole charging situation here. And so, having looked at those curves a little bit, we can say that voltage and charge, which we know are related, right? Because we've said that capacitance is charge over voltage. So if I was to graph voltage over charge like this, then the gradient of this graph here would be the inverse of the capacitance. And so as the charge builds up on the plate, the voltage, so this is voltage on the capacitor. As the charge builds up on the plate, and the actual amount of charge is directly proportional to the voltage, because as we just said, capacitance is a physical thing. It doesn't change. It's determined by the structure of the capacitor. Remember that formula? It's determined by the structure. So there is a linear relationship. Now, we know from our formulas, let's get another bit of paper. We know from our formulas, let's bring that one, that voltage is equal to energy per charge. So energy is equal to voltage times charge. Okay? So if for a particular point of charge here, we've got a particular voltage, then you could imagine if this graph looked like this, voltage times charge, then the area under the graph will represent the energy. So what's our formula going to be for energy in the capacitor? Well, the energy is going to equal VQ over 2 because it's a triangle. Now what V and what Q am I talking about? I'm talking about the final V final, and Q final. So I could call that a big Q. So I actually should write this like that. Because obviously the little voltages and little Q's change all the time until the capacitor that we had at the start is fully charged. Alright. So this graph here, remember when we did this graph? This is the way the voltage is changing against time. Alright. We've got no time element here. We're just saying the way the voltage is changing as the charge changes, and that is linear. The change of voltage against time is not. It's this exponential curve. Now, we've worked out now a formula for the energy. It's VQ over 2. And now we've got that, we could change it a little bit and go, okay, well, V is equal to, we already said that capacitance is equal to charge per volt, right? So charge is equal to CV, so we could substitute that in there. Charge is equal to CV, and we'd have V squared C over 2, right? And we could do the same thing by doing the other substitution, couldn't we? And I've just lost my video for a sec, so I'm just leaning over and doing that. And we could do the other substitution and get the other formula, which would be E equals, let me just bring this up, Q squared over 2C. So we've got 3 formulas for energy. I only really need to remember one of them. I usually just remember that one, and you can derive these other 2 quite simply. Now, the thing is, and this is the thing to watch out for, okay, we've got this formula that says basically, with a circuit like this, the energy to charge the capacitor was equal to VQ over 2. That's the energy. Where is that energy? Well, that energy is in the electric field. The energy is in the electric field. Now, we had an EMF, or a voltage. That's the final voltage. And that's what we said, it's the final voltage times the charge. Right? Now, the thing is, if you work out how much current was flowing during this, okay, the current changed the whole time. All right? But what we can say that only half the energy went into the capacitor. The voltage times the actual current will have been twice that. So that's a little tricky one that can sometimes get you on questions. Realize that VQ over 2 is Q being the amount of charge stored on the sky, and V being the voltage, divided by 2 is the energy to charge that capacitor. The actual current that flowed, half the energy was lost in the resistor. And that's because the basic voltages had to add up the whole time, right? The 2 voltages had to add up. So when this voltage was building up, this voltage was higher. There was voltage in this circuit. It was losing energy in the resistor. So at the end of the day, we can actually say that the energy to charge was V final times Q divided by 2. That half the energy that the battery put out actually was lost in the resistor.